Hi everyone. Today we are going to see about operating system. In operating system we are going to see about deadlock avoidance. So how we can avoid the deadlock? Deadlock can be avoided if certain information about processes are available to the operating system before allocation of resources. For every resource request, the system seems whether granting the request will cause the system to enter an unsafe state. That means the state could result in deadlock. The system then only grants the request that will lead to the safe state. So what are the possible states? No further progress is possible. That is unsafe state, unsafe state. In unsafe state, a state that may allow deadlock. It is possible for a process to be in the unsafe state, but for this not to result in a deadlock. Safe state. A state is safer if it has a bunch of process and there are enough resources for the first process to be finished, and after it releases its resources, there are enough resource for the next process to be processed. There is no chance of deadlock. In order to determine the condition of next state, the system must know these information in advance. Resources currently available allocated to each process, resources that will be required and released by these processes in the future. To avoid deadlock, we have to follow a simple rule. The system causes the next state into say unsafe mode or deadlock, then we should not proceed the request. This is the demonstration that states the safer zone. That is first there should be a free space, and then we have to find the maximum states, and then it is given by the demonstration that states the B is not safe. First one depicts that A is in safe state, and next picture demonstrates that B is in not safe state. Banker's algorithm for single resource. The Banker's algorithm can be used to avoid the deadlock. There are three resource allocation states, that is safe and also unsafe. A scheduling algorithm that can avoid deadlock is known as Banker's algorithm. It is modeled on the way that bankers might deal with group of customers. This algorithm checks whether the request leads to unsafe state or safe state. So Banker's algorithm for multiple resource. The Banker's algorithm deals to handle multiple resource also, where here B is the existing resource possessed and the resources A is the available resources given. So deadlock prevention, attacking the mutual exclusion condition. Some devices such as printer can be spooled. Only the printer daemon uses the printer resource. Thus deadlock for printer eliminated. Not all the devices can be spooled. So what is the principle means? Avoid assigning resource when not absolutely necessary. As few processes as possible actually claim the resource. So when the resource is not needed, then we should not open and have it. And as the few resources are possibly actually claim the resources. Attacking the hold and wait condition. Require processes to request resource before starting. A process never has to wait for what it is needs. Problems. Many may not know require resources at the start of the run. Also ties up resources other processes that could be using. The variation, the process might give you up all the resources, then request all the immediately needed. Attacking the no preemption condition. This is not a viable option. Consider a process given the printer halfway through its job. Now forcibly take away the printers. So this is not a viable option. Consider a process given the printer halfway through its job and now forcibly take away from the printer. So attacking the circular wait condition, image setter, scanner, plotter, tab, drive, CD-ROM or CD-ROM drive. That is normally ordered resources. A resource graph is given here, which is with the directed graph. So what are the conditions and approach for waiting means mutual exclusion will spool everything. Hold and wait condition, will request all the resources initially, no preemption condition, take resources away, circular with condition, order resources numerically. This is a summary of approaches to deadlock prevention. Thank you.